Hello Math 152 students. In this video, we're going to take a look at some topics out of 7.3 and 7.4. We're not going to cover either of these two sections in their entirety, just pick out a couple topics that we're going to need for future chapters. 7.3 is all about assessing normality. And to give us some context for 7.3, I want to show us a homework problem out of 7.1, just so we can contrast. So in this problem, we were given a histogram, and the question was to determine whether or not the histogram indicated that a normal distribution could be used as a model for the variable. Now in this case, looking at the histogram is clearly skewed right. In this case, it doesn't make sense to use a normal curve or a bell-shaped curve to model this scenario. It's pretty clear that this is a skewed graph. So in situations like this where we have a graph, or we have a large enough data set to create a histogram, we just evaluate the graph to make our decision. But the problem comes into play when we have small data sets. For a small data set, you can sometimes not create a reliable histogram because it looks sparse with only a few data points, or even if you can create a histogram, it just doesn't give you enough information to determine whether it could be modeled with a nice bell-shaped curve. So the question we're going to be asking is, how do I know if my data set is normally distributed? If we have larger data sets, look at the graph. Or in some conditions in chapters 8 and beyond, we can assume normality in certain cases with a large data set. But the real issue is, what if my data set is small, less than 30 points? We're going to ask StatCrunch to create what's called a QQ plot. By hand, this is called a normal probability plot that actually plots observed data versus corresponding z-scores and assesses whether the normal probability plot or the QQ plot is linear. Now that sounds like a lot of mumbo jumbo, but we'll get into an example here. Just give us one more summary. For the QQ plot, we're looking for a graph that's approximately linear to say we have normally distributed data. Now I want to show you a picture from your book, and then we'll look at these two examples. In your ebook, we are actually going to go back to chapter 7. We'll come back to this table in a little bit, but we'll go to 7.3. And your book goes through how to do this by hand, kind of in this first example. And then in example 2, what they show you is a QQ plot using StatCrunch. So this is a QQ plot, and what it will do is plot your data points, the expected versus the expected z-scores, and they'll even put in kind of the best fit line for you to assess whether this data is approximately linear. In this case, even without knowing the context, this graph does look approximately linear. So I would feel comfortable saying, this meets the linear criteria. So in this case, if your QQ plot is approximately linear, we would say that the data could have come from a normal distribution. Now, we'll get into the correlation idea in just a minute, but let's look at two other examples. 7.3.8 in your textbook is an example where we're looking at customer service data. Let's actually just go look at the context for 25 data points. So this is number 8. A random sample of weekly work logs at an automobile repair station was obtained, and the average number of customers per day was recorded. So one day we had 26 customers, another day 24, another day 21. And our 25 data points are considered a small data set. We could, if we wanted to, create a histogram, but it's likely to not give us the information we need. So just to illustrate that, don't have a lot of data points. This doesn't exactly look bell-shaped, but it's just kind of iffy. Inconclusive. So what we need to do is create our QQ plot. And sometimes you don't actually have the raw data. They just give you a QQ plot in future chapters. So go back to your graph menu, select your QQ plot, and I'm actually going to check the correlation statistic because we might want that later. So this graph is interesting because I have some repeated data values. Like I have several days where there were 24 customers, and we just kind of see these little rows stack up. Still, to me, this looks approximately linear. We just kind of have some interesting repeated data. Now, I want to do another plot for us with 7.3.10. This actually gives 25 days in selected years of snowfall in a particular city. So we have snowfall in inches. And let's just create a QQ plot out of this one. I'm going to add the correlation statistic and compute. So when I look at this graph, this is a graph that definitely doesn't look like it's linear. We kind of have this funky shape going on where, particularly at the ends, the fit line does not fit very well. So if I were looking at this plot, I'd say, no, not linear. Whereas for the first one, I would say, yeah, it looks pretty close to linear. So how do we make our final decision? It can be tricky. One thing to do is to look at the correlation coefficients. And there is a specific table in your appendix, it's actually table 6, I believe, that gives you critical values for the correlations for QQ plots. So this 0.967, this 0.877, we can compare to that table. Sometimes these tables are a little difficult to find, but let's go back to our appendix. And unfortunately, you can't select the table you want. You just have to scroll through these. Takes a little bit here because the table, some of these tables are a little long. So we're wanting table 6. And notice it says use of the correlation coefficient with normal probability plots. It's a different table of critical values than we were using in chapter 4, but it works similarly. If we had a data set with 25 points, this table indicates that my R value has to be at least 0.959 to assume that the QQ plot is approximately linear. Now, why different critical values than we saw in chapter 4? It's because we're doing those expected z-scores, sort of changing our context a little bit. So they are different values than table 2. But let's compare our critical values in our two examples to that 0.959. In our first example, our correlation value is higher than this, so we're good to go. And in our second example, we're not. So it kind of goes along with our intuition. This one looks okay. I'm okay with saying this is approximately linear, whereas I am not in the second case. So sometimes this can be a little bit tricky. A lot of times we'll be able to make a decision just based off our observation. So let's go back to this one. We know that the QQ plot is sort of subjective. We can look at table 6 to help us out. But another thing we often do in future chapters is take a look at box plots. In addition to having the QQ plot look appropriate, we have an additional condition that you can't have outliers to run some of our tests. So that will be something else we can look at. But we'll save that for a future chapter. In 7.3, I just want to make sure you can create a QQ plot and make a decision. So let's take a look at the rest of our slides here. And we'll go into section 7.4. In section 7.4, we look at the normal approximation to the binomial. And we might be saying, what in the world? I heard of the binomial, that was chapter 6, but let's just recap what that is. We've been talking about normal curves a lot in chapter 7 and haven't seen the binomial in about a week. So for the binomial, remember that there's 4 conditions we have to meet. We have to have the concept of a fixed number of trials, independent trials, success and failure, and the probability of success remaining the same. Those 4 criteria that we saw in Chapter 6. In a lot of scenarios, when we graphed a binomial distribution on StatCrunch, it sometimes looked bell-shaped. Sometimes not, but sometimes it did. So before technology with StatCrunch and graphing calculators, the binomial might have been more difficult to deal with, and the normal might have been an easier distribution to work with by hand. With StatCrunch and with a graphing calculator, we can handle the binomial very easily. But this idea of using a normal curve to approximate a binomial, normal approximation, kind of comes out of the pre-technology days. So sometimes your book will refer to using a normal curve in the binomial situation, and other times we'll just go straight for StatCrunch. So what we want to see here is that for a fixed probability of success with more number of trials, the distributions for our binomial become more bell-shaped. In other words, some of our examples looked bell-shaped because we had a large number of trials. Some of them looked skewed because we had a small number of trials. But the bigger your number of trials is, the closer your binomial is going to look to a normal. And then in those cases, you could switch over and use a normal curve. Now, we aren't actually going to switch over and use a normal curve in practice because we could use StatCrunch for our Chapter 6. But going forward, there's going to be cases where we use the binomial to compute proportions or percents, and then use the normal curve on those percents. So we won't overwhelm ourselves too much with looking at all of that today, but what we want to do is tackle the criteria in which we could use a normal curve to approximate the binomial. And we're going to see this condition again and again in chapters 8, 9, 10, and 11. What we do is look at the combination of the n and the p values. If the n times the p times 1 minus p is bigger than or equal to 10, then you could use a normal curve to approximate your binomial. If it's not, then you're out of luck. So what I want us to focus on is just understanding this criteria. Again, in practice, we could just use the binomial distribution in StatCrunch, but later we're going to see this part over and over again. And just to recap these formulas, these are your Chapter 6 formulas for mean and standard deviation. So what I want to do next is take a look at an example, actually 3 examples. And sometimes we want to be careful because sometimes a histogram could look normal, but we would want to check that criteria. So taking a look at our first example, this is a binomial histogram, just histogram instead of the almost dot plot that StatCrunch created in Chapter 6, but a similar idea. You had a n value of 8, a p-value of 0.15, so 8 trials, 15% chance of success. And if I looked at this plot, it definitely does not look normal. It looks skewed right. So how do we test that criteria? We test that criteria by just inputting our n times our p times our 1 minus p. So I would just simplify this a little bit, stick it into my calculator. Our 1 minus p, you can think about that as the probability of failure. So then when I calculate this, I believe we get 1.02. So just stick it into your calculator. And this value is not even close to being bigger than 10, which kind of reinforces the idea, hey, it's not normally distributed. What we could also do is take a look at 2 other examples. So it looks like we're going to run out of time to wrap up the next 2, start a new video, and we'll take a look at those ones.